to talk to us in person. It's really nice to have in-person seminar. I'm actually saying he probably hasn't done one for 2 years. I'm trying to work out how many I've been to in the last 2 years. It's probably on one hand. So Richard is going to talk about an adjoint aided inference with asynchronous driven differential equations.
What a mouthful.
Absolutely. But I know it's a really good talk because I heard an earlier version online and I said to myself, as soon as I can get him down here, I'm getting down here to talk about it. So Richard, we'll have questions at the end. If you can't read which is writing, or you can't tell the axes on the graph or something, interrupt, but in general, we'll have questions.
I'm happy to be interrupted.
Yeah. Peter, do you want to man the Zoom?
Do I want to man Zoom?
You have to admit.
Okay, sorry, I'm in control.
You're in control.
Oh, right.
Yeah.
This is IDSAI. Right.
Yeah, well, thank you for the invitation. I think I'm looking for my file. I think I last done a seminar in 2018. I gave a rambling kind of talk about why I was losing faith in kind of Bayesian methods, particularly misspecified models. I didn't really have any point to the talk or any kind of suggestions. It was just a moan about things that didn't work. So I thought I'd do the opposite today and just talk about a very specific paper that we've just written and some work I really like. It'll still be rambling, but it's on one topic at least. Okay. So these are people involved in the work. Okay, so we've all part of a big project. Okay, Turn, Gohungu, and Chris Lanyon are the postdocs who've done the work and a joint first author on this work. Okay. So how the project started was engineer Baden Magusha and Mike Smith were both working together in Kampala, capital of Uganda. And they were about the air pollution, and so they wanted to try and measure what the air pollution was, and they came up with a way of creating these cheap air pollution sensors. And they deployed a few around the city. Okay. But because they were cheap sensors, it didn't work very well. And so they think about how should we process this data to say something useful about the air pollution from this cheap, low-quality data. There's then a call by IDSAI for a Global Challenges Research Fund. So this is the government we to redirect its overseas aid budget into research. Okay? And so there's a call to get mathematicians involved in this kind of research. And so the three of us, engineer Maurizio and I, put together this project with Mike. Okay? And this is what we're working on. Okay? So it's based at Nottingham, Sheffield, and Makerere University. The project's slightly cursed in that we started in January 2020. And so all the air pollution sensors we built and we couldn't deploy for a good while because of the lockdown. Then there was presidential elections in Kampala where the incumbent, who'd been there for 40 odd years, shut the city down for a further period and turned off the internet. So that delayed us. And then the government, in part of its cuts after Brexit, slashed all these funding and cancelled all these projects early. So we lost a lot of the funding that we were due to spend due to these cuts. Thankfully, though, we got some more money from Google, I think it was $1 million to carry on this work. So we managed to kind of piece things together. And okay, so I'll tell you about the air pollution problem, what this kind of motivated this problem, okay, why we're interested in these kind of systems. But then I'll abstract it completely, just talk much simply, more simply about just linear systems. So this is where you've got some kind of thing you observe, okay, and you believe that it behaves some kind of linear system. So it's some sort of operator that applies to you, like a differential equation. Okay, and we believe this system is driven in some way. So air pollution, for example, spreads out according to some kind of law, like a diffusion law. Okay? And we want to learn something about what's causing the pollution, so how do we infer things driving this system. Now I'll talk about kind of the technical innovation in this work, which is realizing that if we consider an adjoint formulation, and I'll explain what that means, then we've got some simplification of the statistical kind of methods that we use that allows us to do inference for these problems very cheaply, allowing us to avoid using Markov chain Monte Carlo or other expensive methods like that. So it's a trick that will allow us to do inference quite cheaply. Okay. So air pollution, bad. Okay, it's one of like the main environmental risk factor in human health. The World Health Organization estimates about 7 million people annually die as a direct result of exposure to air pollution. The UK government estimates it's between about 28,000 and 35,000 just in the UK who die as a direct result of exposure to air pollution. Okay. And it costs the UK economy of the order of about 10 billion a year in healthcare, social care, lost opportunities for people being off work and so on. Okay. Air pollution is primarily, or more seriously, a problem in kind of low and medium income countries. So I haven't got onto these numbers, but typically the air pollution here is less than 25, whatever the scale is. Okay, whereas here it's over 165. Okay, and it's bad here, the number of deaths. It's much worse in China, India, Africa. So Kampala has a particular problem of air pollution. So Kampala is the capital of Uganda. And the organisation that we've been working with is the organisation started by engineer, that's his name, Ben Magusha, who one of the co-eyes on the project, okay, and it's called AirQuote. What they've done is develop these low-cost air pollution sensors. So the sensors we use here, these gravimetric sensors, and they typically cost tens of thousands of dollars per sensor. Okay, and we can afford that. In the West, that's fine. We can have one several in each city. We can't afford to do the same thing in many places. Okay, so we've got these low-cost sensors that cost us about $40 to make. We strap them to a lamppost all around the city. Okay? And there is one expensive sensor that we try and use to calibrate the cheap sensors. So the US Embassy has one of these expensive ones. And so what we do, we pay these Boda drivers, these are motorbike taxis. We strap them to the front of there, and they go to the US Embassy, measure what the air pollution is there, then drive to the ones with the lamppost, and we try and use that information to calibrate the entire network by driving around the city like this. Okay. So these sensors measure two different types of air pollution. It doesn't really matter for this talk. And we can use both types of data if we want. These are the kind of maps we get from the data. Okay, so this is Kampala, Lake Victoria. And you, it's down here actually, and you can see the kind of numbers. So on the bottom here is the World Health Organization kind of scale of how bad your air pollution is. Okay, so the UK is generally down here. So the UK average is about 11. Exeter yesterday was 3.1. Okay, so that's in this kind of good zone down here. Kampala, you see most of them in this kind of unhealthy region here. There's a couple of points this day. I forgot to update this slide, but it's just in February one day. Okay? And then we're very unhealthy. So when you get to that level, the World Health Organization advises you don't do activity outdoors, you stay indoors. You know, it's a serious level of air pollution. And it's like that all the time. So this project in a nutshell, this was a tweet by Google yesterday, talking about our project. The buzzword, I guess, is we're going to use AI to reduce air pollution across African cities. Okay, that's the kind of buzzword in kind of description. A bit of a hope, I guess, rather than a reality at the moment. But what we're going to try and do is use machine learning methods or statistical methods to at least say something about what the air pollution is. And if we can say something about what it is and what's causing it, that might be a first step in doing something about it. Other people do it. Okay. So, in terms of the modelling, we're going to think about it in terms of a pollution concentration, U, that's going to vary spatially, so X represents where you are in space, okay, and temporally. Okay. We've got this spatial temporal surface over Uganda. We think about the pollution changing through time and through space, depending on where you are. The wealthier bit, where the US Embassy is and the university, less pollution, the poorer neighbourhoods, higher pollution, and so on. Okay. And the pollution level goes up and down during the day, according to the atmospheric conditions. And what we want to do is try to say what the air pollution is at the moment, as the first step. And then, if we can, try and infer the pollution sources, what's causing the pollution. There's lots of different things that might be causing it. They don't, a lot of the roads are unmetalled, so they're not paved, they throw up dust on traffic lights. People cook on solid wood stoves in many bits of the city. Burning of garbage is common in some bits of the city, as well as all the types of pollution we have here as well with traffic and industry and so on. So there's particular types of things we're interested in. So a standard approach to this might be just use a non-parametric model like a Gaussian process, but we can't answer these kind of questions with those kind of models because they're not able to say anything about sources, pollution sources. Gaussian processes just work in correlation. The name of the project really was how do we build in some sort of physics, the next bit of buzzword bingo, like physics-informed machine learning, yeah? So how do we build Gaussian processes that know something about how air pollution spreads? So what we want to do is build a GP that knows something like this. So the details don't matter here. But this is an advection diffusion reaction equation. What this says is that if you have a bunch of air pollution here, it will diffuse slowly out and spread out. Yeah, it's like a reasonable assumption. That's a diffusion term. This is an advection term, so like fluid gets blown across the city. So if the wind blows, the pollution cloud would move across with the wind. Okay, so that's like a sensible kind of thing. And this is a reaction term that says if nothing else changes, pollution falls out the sky essentially, sticks to trees, dissipates in time and reacts with stuff. Okay. This is a standard kind of approach to modeling air pollution. And what we're going to try and do is say, well, let's suppose we've got some model of the pollution sources, these S's here. Can we say, given the data we have, what these different pollution sources are? Can we learn anything at all about these pollution sources? So here, I've put this as a sum, so we might have different types of source of different pollution types and so on in different regions. But think about the source as being a function we want to learn. It's a function of space and of time. Yeah? Pollution gets created pretty much everywhere in a city, air pollution. Okay? But how much is created varies in space and varies in time. Okay, so the aim is how do we do inference for this kind of model? Okay. So the challenge is that we're going to be given some kind of noisy data. So we're going to have some data Z that is some noisy observations of the pollution concentration U. Yeah, that's what our sensors are going to measure. And what we want to try and work out is what's the concentration field everywhere. And if we do that, what's the source terms? What's driving this? What's forcing this system? And as well, there's other parameters here that we might want to learn. So I didn't mention these, but there's like diffusion rates, advection rates, reaction rates. We want to learn these additional parameters, as well as hyperparameters in any kind of model we use for S. So, probably no surprise to anyone who knows me, but we're going to model S here as a Gaussian process. Okay, so that's just a non-parametric model of a function. We'll talk briefly about that in a minute. So GP here stands for Gaussian process. It's just a model of functions. Okay, we'll talk about it in more detail. And our aim, we're not going to do that in the talk today particularly, but we can, in theory at least, carefully choose the different parts of this model to build an information we know. We know where the power station is. We know where the poorer regions are, where they use home generators are more prevalent and so on. Okay, so we're going to be able to build information in here. But today is just about the kind of mechanics of how we do this and this trick for doing it. Okay. So just to step back then a minute, we'll come back to that example at the end. Let's just think about linear systems in general. Okay, so L, some sort of operator that acts on the thing we measure, U, okay, and it's driven, sorry, I've changed from S to F, okay, by some function F. This is the function we want to learn, our pollution source in this case. What's driving this system? Okay, just the same thing. Yeah, we've got this linear operator which might have some kind of non-linear dependence and so on upon some parameters. Okay, but it's a linear operator. That's key for this talk. Okay. Some sort of forcing function we want to learn, and the quantity being modelled. Okay. And the forward problem that it's often called is given a P and an F, solve this system for you. Yeah, that's solve your differential equation, solve your partial differential equation. Yeah, so that's the numerical method we've used to say what U is given F and L. We're not interested in that. We're interested in the inverse problem, which is given some noisy observations on U, can we say what U, F, and P are? So that's the image one. We want to go backwards. So it tells us some information about U. Go backwards and say, well, what is the system driving this? What's happening underneath it? What is our term? What is our force? Our pollution source? So we can, of course, do this by MCMC. Yeah, it's always possible in kind of problems. You just simulate forward lots and compare what you get and work out the likelihood ratio. And you do MCMC here. But the problem is, in MCMC, it can be very expensive. Because in each step of your Markov chain algorithm, you're going to have to solve the forward problem one time. And if your forward problem is a partial differential equation, it can get very expensive very quickly. If each forward solve takes you a few minutes. So it becomes prohibitively expensive. Okay. So how might we do this? So there's two different approaches we want to think about, okay? And we've got a way of speeding up both of them. The same thing essentially. Okay? One is we might take a least squared or a maximum likelihood approach. So what would that be? That would say, well, let's look at the errors I have with Gaussian here. So that's why it's square. But a least squared would say, look at the sum of squared errors. Given a P and an F, we can solve for U, and then we can work out what the observations would be, that's the U, okay, and work out the sum of squares. That's solving this constrained optimization problem, minimizing the sum of squares subject by linear constraints. Okay. Or we can take a Bayesian approach and say, well, what's the posterior distribution of our parameters, P and F, given the data Z? Yeah. So we're going to help with both approaches here. So in both cases here, it would be kind of useful to marginalize some parameters if that's possible. So that's integrate them out of the analysis. Or compute derivatives somewhere. That would be a useful thing to be able to do. You want to solve an optimization problem, or you want to do HMC here, something like this. So derivatives, marginalization are useful things. And this is where adjoints can help. Okay, so we're going to think about what an adjoint is and how it can help us solve these two problems more efficiently. Okay, so does anyone know what an adjoint is? Peter? Okay. Okay, so this slide is a little bit technical, and I'll state it more simply in a second in terms of Hilbert spaces. Okay, so we've got we're interested in functions, yeah. We've got an operator that maps between functions. So we've got a space of functions U and a space of functions V. And I said they're both Banach spaces here. That means a vector space with a norm, a size, is all that means, yeah? So we can add functions, they remain functions. We can multiply functions by scale, they remain functions. We can integrate functions, that like tells us the size of the function somewhere. Okay. So we've got two Banach spaces, we've got an operator that maps between them. So like a difference equation is an operator between function spaces. We're going to think about the dual of these spaces. So standard kind of notation. So a U star with a dual of U. So what's a dual space? The dual space is a space of functionals. So functionals are maps that map functions to scalars, like integrating or differentiating at a point. Okay, just functional. Okay, and it's a space of functionals that are linear and bounded, which same as continuous. Okay, yeah. So it's just a construct that we can always write down for any given Banach space. Okay. So we're going to construct what the adjoint is, and we'll do it in practice for a few examples, and it'll be easier. Okay. So let's just consider one element of the dual space of V. Okay, so this is a map from functions in V to the reals. Okay. And then I will define a new map from U to the reals, so that's a functional, that takes any U, first applies L to it, and then applies my V star. Okay. So this is a functional, it maps from U to R. It's going to be linear because L is linear and V star linear by definition. Okay. And we can show it continuous, we can show it bounded. Okay. So this is also going to be a bounded linear functional. So in other words, if it's a bounded linear functional on U, it's got to be some element of the dual space in U. Okay. So what we've done is for each element of the dual space on V, we've associated a unique we have to prove these things, of course, but we've so this is a construction associated with a unique element of the dual space of U. So in other words, we've got a map that goes from V star to U star. Okay? It maps the opposite direction of L, but between the dual spaces. And we can show that it is bounded and linear. And this is what we call the adjoint. So we'll see an example in a minute. Once you put your head around the definition, they're surprisingly easy to compute. And kind of by construction of what we've done here, we've got that this obeys what's called a bilinear identity. Okay, it'll make more sense to you than we see in a second, but it basically says that if we apply L star to V star and then apply that result to U, that's the same as first applying L to U and then applying V star. Okay. By construction of what we've done here, you hopefully see that this is true. Okay. This is the key thing we're going to use to derive what adjoints are. The things are simpler slightly, or more familiar, hopefully, in Hilbert spaces. So Hilbert spaces are vector spaces again of functions, but now we've got angle as well as size, norm. So we've got an inner product that tells us angle, it gives us geometry. So it's a particularly nice space of functions. So the nice thing about Hilbert spaces is the dual is the same, the isomorphic to the original space. Okay? I mean, this doesn't certainly matter here, but you can always write any functional as in the product with some V. We don't need to think about the dual spaces. And what happens that's key for you'll say this bilinear identity becomes something you've probably seen before. Okay, so the bilinear identity now is that LU in a product of V is the same as U in a product of the adjoint of L effectively. Okay, so you've probably seen this, if you've seen adjoints at all before, you've probably seen these two bits are equal. So it's kind of slightly simpler setting. So let's just have a minimal example. So in the case we've got finite dimensional spaces, everything's the operators are a matrix times a vector, yeah, in a finite dimensional space. And in that case, you've probably seen this relationship before that the inner product of A, U, and V is the same as the inner product of U and A transpose V. They're both equal to U transpose A transpose V. And just standard Euclidean kind of inner product. Yeah. So with the matrices, you've seen this kind of thing before. So let's have a more detailed example. So this is with a differential equation. I won't derive it from the PE because we expect calculus, but it's the same as this. So let's imagine we've got this differential equation. So we've got U here is just a function of one variable, let's say time, whatever. Okay. And we've got U double dot plus a U dot plus a U equals something. And we've got some initial conditions on U and the gradient of U. So how do we work out what the adjoint is here? Well, let's just write this down as an operator first of all. L of U here is this differential operator applied to U. That's all this says. Okay. And we've got these initial conditions. So it's this operator we want to find the adjoint for with these conditions. Okay. So how do we do this? Well, we start with our bilinear identity and see what we need the adjoint to be to make the bilinear identity true. Okay, so let's start by thinking about the inner product between LU and V. Okay, so what would that be? So I have to take an inner product here, but a typical inner product for L2 okay, would be just the product of these two functions integrated over the domain. Just a standard inner product. And what we're going to do, if we write in a linear operator here, we've got a second derivative and a first derivative. We're going to integrate by parts twice to move the derivative from U to V, and then we'll be able to see what the adjoint is. So if I integrate each of these bits by parts once, I get this expression here. So we get a d u dot v, I go to t and 0, okay, and the integral of the cross term, d u dot v dot, and so on as we go down here. This first term doesn't need to change. Now we know that u dot is 0, at 0. So we're going to be able to cancel out some terms here. But before we do, let's just integrate by parts one more time to get rid of this u dot here. Okay, so I've integrated this bit by parts, so I get an extra kind of evaluation bit plus an extra integral bit, and these two bits are just copied down. So I've just integrated by parts twice. And what we can see, hopefully, is that this operator on V times U, so the inner product between some L star on V and U. And if I pick these conditions, all these bits are going to cancel out, all the bits I don't like. Okay. Just by evaluating V at different bits. Okay. The first time you see it, it's a bit complicated, but it is a kind of undergraduate kind of derivation of the adjoint in the difference equation. It's not too difficult to derive what this is. Okay. And we've set it equal to this because this is what the bilinear identity did. So to make this true, we've had to pick L star in this way. Okay? It's kind of forced our hands to say what L star is. Okay, so just to summarize that, we had this as our original system with these initial conditions. This has become our adjoint system. Okay, but we just derived, but instead of initial conditions here, we've got final conditions. What happens at time t? Okay. So initial conditions are translated to final conditions. So how does this help us at all? Well, let's consider solving this problem. Okay. Let's just consider the simpler case where our function f here depends linearly on some parameters q. And we'll explain how this applies to gas compressors in a minute. So we're going to want to minimize this sum of squares with respect to our parameters q here. And the adjoint is going to allow us just to write down the formula to do that. It's also going to allow us to write down the posterior if we want. And it'll also allow us to get derivatives if we want. Okay? I'm not going to talk about that now. So let's just see one of these cases. Let's see how we solve the least squares problem, the argument case. So let's suppose that our function that we want to learn is a linear combination of some other functions. So a standard kind of basis expansion. Yeah. So it's just s a function of time for a different equation. We're just writing it as a sum of some other functions of time, maybe Fourier terms or something specialized or whatever. It's just a basis expansion. Okay. And let's also suppose that the observation operator is linear. Okay. So for example, let's suppose we just see u at a particular point in time. That'd be a linear observation operator. Or maybe we see the derivative of u or the integral of u. Okay, or something like this, something linear in u. That's mostly what we have when we have observations. Not always. And what we're going to do, we're going to consider n new systems, n adjoint systems. So we're going to consider solving these systems for I equals 1 to n, to indexing across our data points. Yeah, we're going to solve these different adjoint systems. So each one's a difference equation we need to solve. And what we're going to get if we do that is we're going to get our observations, which we said were a linear function of the u's. If I substitute hi for our adjoint system, it's going to be L star of B in the point of view. If I use my adjoint, my bilinear identity, I get this is V with L of U. And L of U, by definition of the system, is just F. Okay. So what we've got is that the observations could be written as, if we wanted, the solution to this adjoint system and our unknown function. It's still not clear how it's helping us at all, but it's just rewritten the problem slightly. Okay. So we've just rewritten it so that our observations are some other solutions that we don't know. Originally, they were a function of one concentration field. Now we've got n concentration fields we have to deal with. So we've made the problem more difficult in me at first glance. The cost of evaluating our likelihood of our sum of squares has gone from needing a single forward solve, so finding u, to requiring n solves of an adjoint system, which is about the same complexity. Yeah. So we had one PDE to solve, now we've got n PDEs to solve, where n is the number of data points. Okay. So it's simply got much worse. The benefits arise if we've got this linear dependence on the parameters. If our function f here can be written as a linear sum, as we often do, then what we're going to get is, because in a product of bilinear, okay, then the cube's just going to come out the front here, and we've got our observations now are just a linear combination of stuff. So we've converted the whole thing to a linear model. We've now got a linear dependence on Q. We know how to deal with linear models as statisticians, whether you're Bayesian, frequentist, or whatever, we know how to deal with these things. So just to rewrite that slightly, we've got that our observations now are some matrix that's formed by inner product between these basis functions and our adjoint solutions, times by a whole bunch of numbers we want to estimate, these coefficients. We can write that as phi q. It's just a linear model. So in other words, we've taken our constrained optimization problem that had some PDE constraint in, and we've converted it into an unconstrained problem. Okay? Now we just need to estimate Q for this system. Admittedly, we've had to solve the system n times, yeah? But we've not got to do it iteratively at all. We've just got a solution we can write down straight away. And second year stats, in Nottingham, we learn, the solution to this system is just given by this. It's a standard linear estimator for linear regression. Then we know how to do statistics with it as well. We can have variances and so on, confidence intervals. So we've done more work, we've done n solves, but we've got the answer straight away. Yeah? Where before we had one costly evaluation to work out the likelihood and then didn't know how to solve the problem. Now we've kind of done n costly evaluations, but we get the answer automatically. We can kind of avoid the need to do MCMC. And the Bayesian approach works as well. Yeah? If we have Gaussian prior, you get Gaussian posterior, and everything looks nicely, we get a Gaussian process posterior, and so on. Okay, I won't linger on that. But the Bayesian approach works as well. So, who here knows what Gaussian processes are? Just, good. Okay. So, let's think about how we're going to do this with Gaussian processes then. Okay, then we'll just be into pictures, results. So let's suppose x is our main function that we want to learn. Okay, so we're going to use a classic process. Let's use a Gaussian process. So to do that, what do we need? Well, we need to specify its main function, its covariance function. Okay, we write things like this all the time, and we know how to do statistics with Gaussian processes. Okay. Why do we like GPs? We have lots of nice properties. Okay. The main one being that they're closed under Bayesian conditioning. Yeah, if you observe a GP of it, it's still a GP. You have a GP prior, you get some data, it remains a Gaussian process. And also our linear, main Gaussian process is under linear transformation. So you can differentiate the Gaussian process, it's still a Gaussian process, you can integrate them and so on. Okay. So there's lots of nice properties. And this is a picture you've probably seen a million times before. You start with some kind of prior specification, so random samples before you see any data. This is kind of how you believe the world might behave, how these functions might behave. You collect some data points, and then you condition the Gaussian process on those data, and you get your posterior mean, your posterior variance, and so on. Standard kind of picture. The question is, how do GPs fit into this framework? Well, what we're going to do is we're going to use a basis expansion for Gaussian process. So again, there's some technicalities here. I won't bore them, but whenever you pick a kernel, K, a covariance function, what you are implicitly doing is picking a space of functions that you believe your unknown function lies in. Okay, called the reproducing kernel Hilbert space, the RKHS. It just specifies a space of functions that are possible with this kernel. Okay. That's just a vector space. Okay, so people can write down bases for vector spaces. So we can think of a basis for this space of functions that described by this Gaussian process. And so one thing people do with Gaussian processes to reduce the cost of them is to think about truncated basis expansions like this. So people do it with random Fourier features, for example, you might have heard of. So this is kind of a widely used approach to machine learning. You're going to truncate this infinite sum that it would be, in general, to a finite sum where you're going to let m be some large number. But the key thing is, we've reduced our Gaussian process here to a linear combination of a number of things. We've got a linear representation, a finite dimensional linear representation of our Gaussian process. So how do we pick basis functions? Well, again, one thing here is there's many different approaches you can use. In some sense, the optimal one is this, the one given by the Carhart expansion, but no one ever uses this in practice. It's a pain to compute. Okay, you have to compute eigenfunctions. So we know what the best thing we can do is this, and it's possible in a small number of low-dimensional cases where we know stuff. Okay, but in practice, we're going to do that. In practice, what we do most often are these kind of random Fourier features. Okay, so they come from a famous paper from Europe in 2005, Rahimi and Rex. We just use Bochner's theorem that says that any stationary kernel can be written as an expectation or a Fourier transform, basically. And then instead of using expectation here, they just randomly pick the random bit. So what a Fourier basis looks like is we just pick random coefficients here and then sum up a load of causal and sine terms, basically. Just a random Fourier, a bunch of Fourier terms. And this is remarkably effective in practice. This is optimal, but you don't need that many more bases, random Fourier bases to do as well as this with any given n. Okay. And we do things on hearts with Laplacian eigenbases, so they live on complex domains, effects on surfaces and so on. Now, let's see how this works here. This is the system we tried before, our one-dimensional difference equation, our original system, our adjoint system. We're just going to write our Gaussian process as a sum of cosines. Okay. And then we know from the work we did before that the observations just become a linear combination of the adjoint system solved in a product with those cosines. So we're going to take inner products of our adjoint solution with cosines. That's fine. It's easy to do. Okay. And once we've done that, we get the posterior for free. There's some examples here. So I picked up, what we're looking at here is the random forcing function f for this differential equation. Okay. So I picked a random f, that's the red curve there. And then I've simulated, Paterno and Chris have simulated U, and we've got some observations on U, on the solution space, on the concentration field, if you like. And then what we've got is the posterior in each case. So in this case here, we had 10 data points. Here we've got 100 data points. Okay, and you can see having more data points is better than having fewer. It's quite a practice, yeah? But we're kind of learning the right posterior. And the key thing is here is the amount of work we have to do. To get this posterior, I needed to solve 10 differential equations. To get this, with 100 data points, I had to solve 100 different equations. We can't get near these posteriors using MCMC and the forward solution. You'd need thousands of iterations at least. Okay. We can't do anything with 100. Here's what happens when we change the number of basis vectors. So here I had 100 data points and 100 basis vectors. Here I didn't use enough basis vectors. I've only got 10 basis vectors. And you can see we're misspecified. We're overconfident we're wrong because our model isn't sufficiently rich. I've reduced this Gaussian process down to a linear model with 10 coefficients, and that wasn't enough. Okay. So we needed 100 or more basis vectors. But the nice thing is here, there's essentially zero cost from having more basis vectors. I mean, there is a cost, but there's no more ODE solves required. Okay. We have to solve a linear model with more parameters, but solving linear models is cheap. I can do that with 1 million parameters. They still both require the same number of ODE solves, 100, but it doesn't matter how many basis vectors. So we can play around with that for parts and 10. We don't have to do any more simulation. We can fiddle with the number of basis vectors, the choice of basis vectors. All of that is, the adjoint system is agnostic to that choice. It's decided after the end. So we've got this cost of doing the adjoint solves, and then we can play around with the other bits to get the answer. Okay. So just to show we get the same answer here, let's do it with MCMC. And you can see in this kind of fairly simple MCMC example with 10 features only, we needed several thousand iterations to get convergence. Okay, I'm sure we can improve that slightly. But what happens with MCMC is you get bigger parameter spaces. If I went to 1,000 basis vectors, I'll have 1,000 parameters to learn by MCMC. Again, we'd need more and more iterations typically with MCMC. The higher the dimensional space, the more iterations we're going to use. Okay. So I'll just show results on the PD example, and then I'll shut up. Okay. So this is our reaction, diffusion, advection equation that we started with. This is our forward system, and we had some initial conditions. You can look in the paper if you want to see how we derive the adjoint. I'll write it down in the middle in a minute. But what we're going to assume is that this system is driven by some unknown pollution source. I'm going to model as a Gaussian process. I'm going to truncate it just as before, and then we're going to assume we've got observations. And what our assumption for the observations is that the sensors average over a period of time. We get better observations if we average over an hour. So we're just going to integrate our solution space over an hour. So these are just indicator functions to capture that, basically. Okay. We just integrate over some small time interval. Okay. So if this is our original system, what we're going to have to do instead is solve n different adjoint systems where n is the number of data points we have. So that might be a lower number, but we're still going to argue it's better than MCMC in many cases. So the adjoint, the details don't matter here. It looks pretty much the same, okay, as before. We just got a few minus signs. We've got some slightly more complicated final conditions, but it's the same kind of process. We did exactly the same integrating by parts twice, essentially. It's just we have to use Green's theorem to do it because they're all vectors over there. Okay, so just to show you some results. Here we just got to experiment with very small amounts of data. So here is the kind of the ground truth simulation. So we take this as our pollution source, we simulate our concentration field that after it's passed through the advection diffusion equations. And then we've said, what can we do if we just have 4 sensors? There they are. So I think we've said here we've got 5 observations from each of 4 sensors. Okay? And this is our posterior we get here. If we have 16 sensors with 5 observations from each of them, then we get this posterior mean for this. So you can see with 4 sensors we haven't quite learned what's happening. We've learned something. With 16 we're doing much better. This here is posterior variance. And the wind in this example is blowing from the southwest. So you can see that we are less uncertain down upwind of where the of the sensor. Okay, wind blowing this way, so we're more confident of what's happening in the pollution there than we are behind it. And again, this allows us to play around with things. So if we change the length scale of our force pollution, things get harder. You probably can't see these graphs, but yeah, it basically gets harder as you get shorter length scales for obvious reasons. You need more information to learn a very short length scale, but we can still do things. Okay? With 1,000 data points, all we need is 1,000 solves. Still cheap compared to MCMC. Okay. And you can look at those numbers in the paper. Okay, but we've got results and numerical things and so on. We've also got non-linear parameters, so they were like the diffusion tensor, the advection direction, which we can kind of infer from the wind anyway, the reaction rate, GP hyperparameters. So we've got various ways of estimating these. The easiest way is like Bayesian optimization, you know what that is. It involves more Gaussian processes. Okay? But the nice thing is that we can also get the adjoint sensitivity. We get derivatives. Okay, we can get derivative information that's going to help us do the parameter estimation bit better. Okay. That's not in the paper, we'll go on the next paper. Okay. So just to summarize then, the costs here. So for this adjoint approach, if we've got n data points, we have to do n solves of our linear system. N solves of your differential equation. Okay. We've got a method that's essentially insensitive to the number of basis vectors or which basis vectors we use. You can change them after the event, it doesn't really change anything. It's not going to affect your cost. We've got a problem with the non-linear parameters. You have to deal with them in a slightly awkward way at the moment. The competitor method, I guess, would be MCMC. The nice thing about that is you can infer everything at the same time in kind of a nice approach. But the difficulty is it's hard to say how many iterations you're going to need. Typically, for a PDE like this, you're going to need thousands, if not several million iterations, and it still might be a mess at the end. They want to click down to see it. It's a nightmare to get it to work often. Okay, so this allows us to avoid this. Okay. So, just to conclude there, I guess this is an intrusive method. Yeah? You need to know a little bit of maths to be able to work out what the adjoint is. You need to be able to implement the model yourself. It's not a black box method like MCMC is or a Gaussian process emulator would be doing it that way. This you need to be able to get into the equations. And the system has to be linear. The nice thing is it gives things like stable derivatives and it gives us the exact Bayesian posterior for the approximate models for free. Okay, so we kind of don't have any convergent words or anything like that. We get that for free. And I think we're working on lots of different ways at the moment to kind of improve this. So how can we do the adjoint simulations more efficiently so we don't have to do quite so many? There's ways to get big savings there. Multi-level approaches. If you've got PDEs, we can solve them at different discretizations to reduce costs and kind of weight. So if you're interested, we just had the paper accepted to NeurIPS for December, and it's on archive already. So yeah, please have a look. Otherwise, thank you for listening.